Eyes are the windows to our world. So goes a famous quote. But what if there is something wrong with our eyes? What if we can't see properly? Then we usually go to the doctor. We go to the eye doctor, and the doctor makes a diagnosis about our eyes. Now, what if we could automate that diagnosis of the doctor? What if we could add artificial intelligence to the diagnosis of the doctor? So this talk is about how to use deep learning for retina segmentation. We are going to talk, in the first part of the talk, we are going to talk about the prototyping of a deep learning algorithm. In the second part, we will talk about how we brought that deep learning prototype to production, how we made it available to specialists around the world. Now, who are we? My name is Kaiser. You can see me here. I'm a software engineer working for supercomputing systems in Zurich. And you can see our team here of people who are involved in that project. My colleague Suter is also here today. She will give the second part of the talk to you in a couple of minutes. Now, the project which we talk to you about today is a collaboration between the IOB, the Institute of Molecular and Clinical Ophthalmology in Basel, and Supercomputing Systems, the company I am working for. Basically, the IOB is our customer, and together we want to achieve the following goals. We want to support ophthalmologists with artificial intelligence. Now, ophthalmologists are eye doctors, and we want to provide those ophthalmologists with an AI-based system for that they can do automated retina segmentation of retina images. By this data, we want then to detect irregularities in eyes, and we want to do volumetric analysis. And basically, we want to make that system available to the public. For that, it can not only be used by one doctor, but by doctors around the world. These are our goals. Now, what kind of data are we working with exactly? You heard in the introduction we work with optical coherence tomography images, OCT images. Let me explain shortly to you how those images are generated. So here on the left side, you see an eye. In the middle, you can see an OCT device. Now, that OCT device sends a laser beam to your eye, and the laser or the light is then reflected back to the OCT device. By the way, it's not painful, even though it might seem so. I did it by myself. It's quite a convenient procedure. Then by the light that is reflected back to the OCT device, the device is actually able to assemble a 3D image stack that can look something like that. So that stack, which you see here on the right side, represents basically the part of your eye that is indicated by this blue box here. So it's the back of your eye, which we are looking at. And at the back of your eye, there are many interesting structures. The retina is one of them, but also the optical nerve. So if you really have a problem with your eyes, the ophthalmologist usually looks there. He takes those images and looks there whether there is something wrong. Now, when we work with those images, usually we rotate them by 90 degrees, and we look at them in this orientation. This is just for convenience. Somehow the images are easier to look at in this orientation. And if you look at the images, you see that there are different layers or different compartments, as we call them. They have names. One of them is the retina, which you can see here in the middle. There are other 3 compartments which are relevant. I will not go into the details about those compartments because I'm not a medical doctor, but let me just tell you that the ophthalmologists, they use the geometry of those compartments to determine whether your eye is healthy or not healthy. Now, what we want to do is we want to take that stack of images, we want to train a convolutional neural net, and as an output, we want to get pixel-wise segmentation maps. So as an output, we want to know of each pixel to which of the compartments it belongs to. That's our aim, so to say. So our approach is to train a CNN for OCT segmentation. Based on that data, we want to detect irregularities, and we want to perform volumetric analysis of your eyes. And these steps, which you see here on the slide, they are all part of the prototyping. That's what I'm talking to you about right now. In the second part, as I already mentioned, Susan will talk to you about how we brought that prototype to production, how we turned this data science prototype into a productive software that can be used by doctors and specialists around the world. She will mainly be talking about the decoupling of components and how we deployed everything to the cloud. Now next, let's talk about the ground truth. For our project, we had to generate the ground truth by ourselves. It was not there to start with. We had to generate labels somehow for our images. And first of all, we decided to work with 2D images. I mean, basically we had those 3D image stacks of OCT images, but we decided to work with 2D only to reduce the complexity of the task. And then we had to generate the labels somehow. So what we did is we asked an expert ophthalmologist to label the OCT images. And the process of labeling is indicated in the bottom of the slide here. So we start with a raw OCT image, and then what the ophthalmologist did, he drew lines to separated compartments from each other. You can see here on this slide we have 3 lines, an orange one, a blue line, which might be a bit difficult to see, and a yellow line. So by drawing these lines, the expert ophthalmologist, generated the ground truth, so to say. And in the last step, we converted those lines into pixel-wise segmentation maps, which you can see here on the right side. So finally, we ended up with a ground truth set that contained roughly 5,000 training images, around 1,200 images in the validation set, and 60 images in the test set. Let's move on to the neural network architecture. For this task, we decided to use a UNet. A UNet, I guess some of you are familiar with the UNet. It's a neural network architecture that is often used in semantic labeling tasks for medical applications. I mean, the name UNet, the U in UNet derives from this U shape, which you can see here. And basically, what we do is we take raw OCT images, we input it to the net, then it's processed through the net, and as an output, we get these semantic segmentation maps. And we didn't take the original UNet, we had to make some modifications to it. Most importantly, we had to add one more layer in depth. This is indicated by this step here, and we did that to increase the receptive field of the net. That was necessary for us to get better predictions. Good. Now, I would like to talk to you about the performance of this UNet, of the CNN. So we evaluated the predictive performance of the CNN on the test net, and the results you can see here. This plot is called the multidimensional scaling plot. It's basically similar to PCA, to principal component analysis. Let me tell you what you see here on this plot. So what you see here in blue color is actually are the predictions of our CNN algorithm. And in red, in those red squares, you can see the ground truth labels of the test set. Now this plot basically visualizes the similarities between different labels. If we have 2 points, and if they are close to each other, that means the labels which they represent are similar to each other. If the points are far away from each other, then the labels which they represent are different from each other. Now you might ask yourself, why is there one CNN? Why is there 1 point for the CNN, and why do we have 3 ground truth points? Usually we only have 1 ground truth set, so we would only have 1 similarity between the ground truth and the CNN. In our case, we asked the expert ophthalmologist to label the test set the 2nd and the 3rd time. So we have 3 samples of the labels of the test set, and you can see them here on this plot. And interestingly, there is variability in the ground truth. This ophthalmologist, he labeled the test set images differently each time. And this is an interesting case in machine learning. In machine learning, we call such a situation where we have an irreducible error. That means there is not one ground truth that is correct, but there are like multiple interpretations of the ground truth that can be true. And you can see this here indicated by these 3 red G's in this plot, actually. And interestingly, I think we can say that the blue CNN gets pretty close to the red points. So I think we can say that the CNN gets close to the irreducible error. In such a situation, that's what you want to have. You want to have a CNN or a machine learning algorithm that copies your ground truth almost perfectly. And I think we have achieved this in this setting, as you can see in this slide. Now we wanted to investigate further in the variability of possible ground truth labels. So we asked another 3 ophthalmologists to label the test set. And you can see the results here. So these are 3 additional doctors. They are different from the doctor or from the expert who generated our ground truth. These are different people. And we didn't use the data which they labeled as training data. We only asked them to label the test set to see the variability among possible ground truth labels. And you can see the variability is quite large. Doctor 3 generated similar labels to our labels, but Doctor 2 and Doctor 1 generated quite different labels. Additionally, we asked so-called reading center experts, indicated by the C here, to label the test set again. Reading center experts are people who on a daily basis grade or see such OCT images, so they are real experts about understanding OCT images. And you can see their labels here on the plot by C1, C3, and C2, and again we see variability. Now finally we asked amateurs to label the test set, so people who have not been exposed previously to OCT image labeling. They just got a short training by an expert. And their labels, you can see them here, A3, A1, and A2. There is also variability. But interestingly, they are not outliers in that plot. You might expect that an amateur would kind of label very differently from the real experts, but that doesn't seem to be the case. Now to summarize these findings and also to summarize the prototyping, which I'm talking about right now, I would like to say that the CNN, I think we can say the CNN, the blue CNN, gets close to the red points, it gets close to the irreducible error. But on the other hand, there is a large variability between the labels that different labels assign to this data. And there is even some intra-labeler variability, I mean, among the labels, which one specialist assigns to the labels. And this is a very interesting point if you deal with medical applications. I think in medical applications you often have the case where you don't have one golden ground truth that is true, but you have some variability among the possible interpretations of the ground truth, so some different truths, and you have to think. If you train a machine learning algorithm as a data scientist, you have to think from which ground truth do you want to learn? Do you want to learn from one doctor only, or do you want to kind of learn from a consensus of other experts? So that concludes the first part, and now let's hear from Susan how we turned that prototype into a productive software.
So thank you, Pascal, for showing us the results on our study. I will now look or show you what machinery we had behind in order to produce the data that generated these results. Now, what components did we use? So first, for the prototype, we had 2 components. One was a web tool that we specifically developed in order to generate that these ophthalmologists could generate the lines, and we had labels available for our training. And the second part, what we had is we had a CNN training and testing component. This was a local GPU server where we inputted both labels and original images and traded until we were satisfied. Now, once we had folded our paper plane, we wanted to make it a real plane and make it available to the people. And for this, we mainly performed 2 essential steps. The first step is that we had to decouple our components. We had the training phase, and there we extracted our CNN model and used it only for the prediction. And then new data could be inserted into this predictor, and it would generate us the segmentation. As a second part that we use for these ophthalmologists is that they want an automated analysis, and we mainly perform volumetric analysis such that ophthalmologists can compare between different points in time, before or after surgeries, how these different compartments change or become better. And for this, we generated some statistics. Now, the second part, or let's say these components were still local, and for us it was important that the ophthalmologists can access these tools, but they are not used to work with GPU servers. They need some sort of an interface, and that's we deployed it to the web. And so the first step was, or the second step was the deployment, where we actually have a backend that does the CNN prediction and the analysis. This we did it as a cloud service. We used I can show you later. And the second thing is that we had a front end, which was again a website, a web service, where ophthalmologists or researchers can upload their data. And they also have to indicate information on volumetric physical dimensions. And then they receive the segmentation and statistics out of that. We connected these two components through a REST API, where the front end just can make calls to the backend and retrieve the data. The backend, we deployed it on a Microsoft Azure Cloud VM with a GPU, because we wanted, similar to the previous speakers, we want to reuse available services, and especially also it reduces maintenance. Then we containerized it such that it is easy. If we want one day to change away from Azure Cloud, we can easily deploy it on a different system, so we used a Docker container. And then we had 3 components where the OCT service basically provides this REST API to the segmentation and analysis services, which are easily accessible. To conclude, what were our learnings? One thing is that it's very challenging with one CNN to cover the full input range of data. That was also already as mentioned previously. We had training data from 2 different instruments. Now, if a third instrument comes, this will be a different challenge again. And there were different sizes of image input data which we had to incorporate. We also realized it's very important that we have a versioning of our segmentation output. If ophthalmologists generate data, and then they have it with them, but maybe next time we have an updated version, and so they should still be able to compare their results. And then we decided also for costs reasons and maintenance reasons to go for the cloud and use existing services. And then with medical data, it's always a question of data security. In our case, the users decide what data they upload, and we have no patient data uploaded. Of course, it's a question, is the eyes are somehow biological data? That's a question still to discuss, but that are some of our learnings. To conclude, we have now an automated, reproducible image segmentation system for retina images for the moment, and it's available to non-tech users. For the moment, we have this compartment analysis, but we are also working on tumor analysis or retina layers, so there will be many more things to come. We evaluated a test set where we showed that the variability between users is actually larger, and compared to that, the CNN is on par, and it always produces the same results. So finally, to conclude, we know it's a small step, it's not a global solution yet, but it's easily accessible, and it's a start, and maybe a start, as Pascal mentioned in the beginning, to look into the eyes or the souls more closely. With that, it concludes. Thank you.
Thank you